Hi class, I hope that you are all doing well. We're getting into part 1, drawing structures of organic molecules. You will find that in the first few chapters, it's going to be partially review from GenChem and partially new material. But beyond the first, I think 4 or 5 chapters, there's going to be a very dramatic shift towards new material. So please keep yourself up to date on these videos so that you do not get left behind. It is very easy to get left behind in OChem, which is why a lot of students believe that it is a challenging course. Let's first discuss the octet rule. Atoms are going to transfer or share electrons in order to have the same number of electrons as the closest noble gas atom. And that's because these noble gas atoms are so insanely stable because they have a completely filled valence shell of electrons. Most of the time, this completely filled valence shell of electrons refers to having 8 valence electrons. That's why this is known as the octet rule, because oct usually stands for 8. And we do have exceptions. For example, with hydrogen, its closest noble gas atom is helium, so it only needs 2 electrons. And boron and aluminum, these are stable with only 6 valence electrons. We think of them as incomplete but still stable. And elements beyond the third rule, which we don't talk about at all in OChem really. We discuss those elements more when you take inorganic chemistry. So these have an expanded octet of more than 8 electrons. So don't really worry about those that much, even though we are going to touch on it slightly. We talked about atoms transferring or sharing electrons, and these result in different kinds of bond formation. For example, if you decide to transfer electrons, what we form would be known as ionic bonds. This is generally going to be between a metal and a nonmetal. Let's look at an example here, right? So atoms are trying to satisfy the octet rule by transferring electrons from one atom to another. So we have lithium, which is a metal, and chlorine, which is a nonmetal. So chlorine would like one additional electron, and lithium happens to have that one additional electron to give. So what ultimately happens is that you have 2 ions. So lithium has the same number of electrons as helium, which is a noble gas. So lithium ion is stable, and chloride ion is also stable. And because one is positively charged and one is negatively charged, these two are going to attract one another, ultimately resulting in ionic bond formation. So when exactly do we form these ionic bonds? The more electronegative an atom is, the more it is able to attract electrons. And electronegativity increases from the left to the right. Oh, whoops. So it's going to go from the left to the right of the periodic table and from bottom to the top of the periodic table. So chlorine is right here, right? So chlorine is pretty electronegative, so it's able to pull the electron away from lithium. And generally, you will see that ionic bonds, they're going to form when the difference in electronegativity is greater than 2. So let's look at lithium, it's 1, look at chlorine, it's 3. So the difference is 2.0. I've seen it being slightly different in different textbooks. I've seen 1.8, 1.6. So just know that usually if it's between a metal and a nonmetal, you will form an ionic bond. It is also possible for atoms to share electrons. And when they share electrons, you end up forming covalent bonds. This usually happens between two atoms that are both nonmetal. So let's look at an example. Let's say we have two chlorine atoms together, right? So instead of transferring electrons, right, transferring electrons here wouldn't really help one of them. It might give octet to one of the atoms, but it wouldn't help both of them. So you can end up sharing one electron pair in the center. I'm going to draw this overlap. Right, so the two electrons here are being shared by both chlorines. You can also draw them differently here in OChem. You don't have to draw all the electrons. You can just draw a bond between the two and then fill in the lone pairs. This can also happen with, let's have another example. Let's say we have hydrogen as well as chlorine. And that can give you HCl. So you can represent the pair of electrons that's being shared between the two atoms as a covalent bond. Covalent bonds are generally found in atoms that are closer together in terms of electronegativity. In OChem, you'll see that we're going to spend a lot of time on carbons, nitrogens, oxygen, halogens, and hydrogens because they form covalent bonds. Most of the time, we're not really going to touch on ionic bonds in OChem. So let's see how these 5 different kinds of atoms form bonds, covalent bonds, when they are neutral. This is especially important because the numbers for the number of bonds that they can form, it's going to change when you throw in formal charges. Let's first talk about carbon. It's in most organic compounds, and it has 4 valence electrons. So if we were just drawing the carbon atom, right, this is the 4 valence electrons. You wouldn't pair those electrons up unless if you had to. And you need 4 more electrons to complete octet, meaning that you have to form 4 bonds, 4 covalent bonds. I'm going to circle this number 4, and these 4 bonds can come in the form of all single bonds, right? Or we can throw in 1 double bond or 1 triple bond. So all of that would give us carbon with octet. We also have nitrogen. So nitrogen has 5 valence electrons. So now we have to pair one up. And in order to complete octet, you need 3 additional electrons. So we're going to try to look at the different combinations again. So we can have 3 single bonds, right? So that would give us the 3 bonds. Or we can include 1 double bond and 1 single bond. That would still count as 3 bonds. Or we can just use 1 single triple bond. That will also give us octet for nitrogen. With oxygen, we have 6 valence electrons. So 2 pairs. And in order to achieve octet, that would need 2 additional electrons, meaning 2 bonds to the oxygen. So that would mean that we could have 2 single bonds potentially, or 1 double bond. So you'll see that we're having less possibilities as we see that the number of electrons needed to complete octet goes down. With hydrogen, something that we're pretty familiar with, it's number 1 on your periodic table. It has 1 valence electron and we'll only need 1 additional electron to complete octet. So we only have really 1 option, right? All we can do is form a single bond. That's it. We can't really do anything else. And halogens are pretty similar to hydrogens in that sense. We're going to use chlorine as an example. So any halogen will have 7 valence electrons, and it needs 8 to complete octet. So it really only needs 1 additional electron and therefore 1 bond. So halogen and hydrogen, both of those 2 kinds of atoms, will only need 1 additional covalent bond. So this entire table can be distilled into the HONC 1, 2, 3, 4 rule. H in HONC refers to hydrogens and halogens, so they can only make 1 bond. Oxygen makes 2 bonds, nitrogen 3 bonds, and carbon 4 bonds, which is why it's called the HONC 1, 2, 3, 4 rule. So in a pinch, if you can't remember how many bonds carbon needs to have octet, just remember HONC 1, 2, 3, 4, 4 bonds for carbon, and then you make sure to give it that 4 bonds to give it octet. That's something that you'll see over and over again in OChem, because usually in OChem, we will always have octet for these elements that we're working with. It is also very likely in OChem for carbon, nitrogen, or oxygen to have 4 more charges, meaning that it could have a positive charge, making it cationic, or it could have a negative charge, making it anionic. When you have charged molecules, the number of bonds are going to change. So HONC 1, 2, 3, 4 does not apply here because that's only for neutral atoms. So carbon, when it's neutral, it's going to give you 4 bonds. However, when it's cationic, it's going to be called a carbocation because of that positive charge. And instead of having 4 bonds, it's going to have 3. These carbocations are pretty special in OChem because if you look at the carbon in both of these instances where they have 3 bonds, we do not have octet. So there's no octet here. There's only 6 valence electrons. That's why carbocations are special. They're usually the only atoms we see in OChem that don't have octet. Moving on to carbon as an anion. So that is called a carb anion. With carb anions, you also have 3 bonds, much like the carbocation, but the difference here is that you also have a lone pair. So the lone pair contributes to the octet of the carbon. So the carb anion actually has 8 valence electrons, giving it octet. And you'll see that with carbon, like on the previous page, as long as you have 3 bonds that are there, it doesn't matter if they're all single bonds or if it's a combination of perhaps double bond with a single bond or just a triple bond. All of these are fine as long as you have 3 bonds that are attached to the central carbon. Let's look at nitrogen. When nitrogen is neutral, it needs 3 bonds to have octet. Now put on a positive charge on that central nitrogen atom. you have a positive formal charge, then you need 4 bonds to have octet. So that could be any combination of single bonds with multiple bonds. So you can see that in these 3 examples, we have 4 bonds in all of the cases. And moving on to when it's anionic with a negative charge, then you're going to have 2 bonds instead of 4, right? So in both of these cases, you see that you have 2 single bonds or just 1 double bond. And with oxygen, if it's a neutral atom, it forms 2 bonds to get octet. And if it's cationic with a positive charge, it needs 3 bonds to have octet. And when it's anionic, it needs 1 bond to have octet. I include this table here because some students like memorizing things, right? So you do have that option. But I will say this over and over again in this course, with OChem, if you have the option, always try to understand it instead of memorize it. Because if you try to memorize everything, there's a lot to memorize. But if you understand it and internalize it, then it will be easier for you to understand the knowledge that you're trying to learn. So let's take some time and understand this table. Let's break it down. We know that with a neutral carbon atom, it has 4 electrons in its valence shell. So with the carb anion and the carbocation, that's going to be a little bit different, right? So with the carbocation, C+, it has 3 valence electrons, right? We're removing 1 electron. And with the carb anion, it's going to have 5 valence electrons because we're adding 1 electron. So let's draw the carb anion, right? So I'm going to draw it this way because it looks very much like a neutral nitrogen atom, okay? And think about your Honk 1, 2, 3, 4 rule, right? Nitrogen can bond to 3 atoms. So a carb anion, because it has 5 valence electrons, it's going to also bond to 3 atoms. So the carbocation, it's in a league of its own because it doesn't have octet. So that's just going to bond to 3 atoms. With neutral oxygen atoms, there are 6 electrons in their valence shells. With an O+, we're removing 1 electron, so it's 5 valence electrons in the cation, and we're adding 1 electron for the anion, so that's 7 electrons in the anion. Let's first look at the cation. It's also 5 electrons. Right, so the oxygen with 5 valence electrons, that should remind you of the carb anion right above it, this guy right here, right, also 5 valence electrons, as well as the neutral nitrogen atom. So they're going to behave the same way because all of them have 5 valence electrons. So they can form 3 bonds to 3 atoms. And looking at the oxygen anion, it has 7 valence electrons. Do we know anything that we have learned so far that has 7 valence electrons? We do, right? So all the halogens that we've seen so far, they have 7 valence electrons. And they form 1 bond. They form 1 bond to an atom. So similar to halogens. So what we're doing in this table above is we're just trying to find similarities between the cation or the anion with the neutral atoms from the previous page. If it has 5 valence electrons, it's going to behave like a neutral atom that has 5 valence electrons, even though it has a positive charge. So always try to understand what's going on here. I'm going to leave the nitrogen up to all of you. I want you to take the time to fill it in yourselves. Try to understand it instead of just memorizing and regurgitating. So if you have an N plus and an N minus, what's it going to be? Fill in everything else on your own as practice. In organic chemistry, we talk about formal charges a lot of the time. Formal charge isn't on the entire molecule. Instead, it's on specific atoms. There is a shortcut to calculate formal charges. The formal charge of an atom is going to be equals to the number of electrons in the neutral atom minus the number of electrons an atom currently has. Let's box that up. And one big thing I want us to pay attention to is that we are only counting one electron from each bond. So we are not counting both electrons. Let's do some exercises. Let's say that we are given this molecule here, and I ask you to just tell me the formal charge of the carbon that you currently see. Let's try to apply this formula. In order to find the formal charge of carbon, we have to first take the number of electrons in the neutral atom for carbon, which is 4, minus the number of electrons an atom currently has. And we're only counting one electron in each bond, so I'm just going to draw dots for the electrons that I am counting. So it's going to be 4 minus 4. So it's going to be 0. Now let's do the same thing for nitrogen. Number of electrons in the neutral atom for nitrogen. Start here. That's going to be 5 for nitrogen. And number of electrons an atom currently has. That's going to be 1, 2, 3, and then 4. So we're going to do 5 minus 4, and that's going to be 1. Meaning that this nitrogen currently has a formal charge of +1. So you have to draw a plus charge next to the atom and then put a circle around it. The circle is important because sometimes we have negative charges and they can look like bonds. So we want to make sure to draw that circle so we don't confuse ourselves or someone who's reading whatever you're writing. I also want us to do it for the oxygen in this molecule. But before I go over it, I want you to pause the video right now and just try to write it out on your own. So pause the video right now. If we're thinking about the number of electrons in a neutral atom for oxygen, that's going to be 6. And we're going to subtract the number of electrons an atom currently has. So just know that in OChem, we don't always draw all of the electrons. I know in Gen Chem we always do, but in OChem, as we move forward past maybe the first semester, we start drawing less of these lone pairs because we assume that you know what's going on. So if we're counting the number of electrons, make sure you draw in all of the electrons and you're not just missing some because it's not shown in the molecule. So it has 7 valence electrons, which gives it a formal charge of -1. So oxygen then has a negative charge. You can see that these molecules can have more than one formal charge in one molecule. And if you're looking at this molecule here overall, you would say that the net charge is neutral. We would consider this to be a neutral molecule, even though it does have formal charges on separate atoms. Usually during the semester, I use something called Plickers to monitor student learning. Since we're learning online, it's a bit harder for us to do this, but I'm still going to include these mini problems during our lectures so that you have the choice of pausing the video and just working on these problems to make sure that you still kind of know what's going on as you listen throughout the lecture. And let's face it, if you're listening to a lecture for an hour, it gets boring, right? So stop it every now and again, do a couple problems, and then it refreshes your attention span. So I'm going to have all of you work on a problem. So let's do some exercises. I have a portion of a molecule drawn out for you here with no visible formal charges. So I want you to calculate the formal charges for the carbon, oxygen, and the nitrogen. So you have the options here, +1, 0, and -1. Very rarely do you see anything that's +2 or -2 in OChem. I've never seen it in my years of doing things with OChem. So pause the video right now and take a stab at it. Let's first look at the formal charge for carbon. We always want to start with the neutral carbon, which is going to be 4, minus, in this case, let's count the number of electrons directly on the carbon. So that's 4, right? Because you only count 1 electron in that bond. So the formal charge of the carbon is going to be 0, which is B. Now let's look at formal charges for oxygen. Oxygen usually has 6 valence electrons. And in this case, we have 1 electron pair that's not shown. We're going to count everything else. So 1, 2, 3, 4, 5. So you get +1 formal charge. So for oxygen, it's going to be A. And finally, formal charge for nitrogen. Usually it has 5 valence electrons. In this case, 1 pair of electrons is not shown. And it has 5 electrons. So again, this is a neutral atom, so it's going to be B. And if you want to also use the Hunk 1, 2, 3, 4 rule here, you will also be able to see that, if it's 4 bonds, carbon is going to be neutral. If it's going to be 3 bonds for the nitrogen, it's going to be neutral. You can also look at it that way, but it's usually pretty easy to just go through and do the math for it as well. But it's usually pretty easy to just go through and do the math for it as well. There are, however, some fascinating exceptions to the octet rule. The first one is that third row and higher elements, they have d orbitals, so they can extend their octet in their valence shell. For example, we can see this in sulfuric acid, H2SO4, as well as in phosphoric acid, H3PO4. Specifically in the sulfur and sulfuric acid, if we count the number of electrons it has 1, 2, 3, 4, 5, 6 bonds. So the sulfur has 12 valence electrons. So that's an expanded octet. Phosphorus, same thing. It's also beyond the second row, so it's third row and higher. So if we count the number of electrons, it has 1, 2, 3, 4, 5, 10 electrons. So both sulfur and phosphorus are happy right now, even though they don't have 8 valence electrons. They both have expanded octets. We also have atoms with open shells or incomplete octets. In general, atoms in group 3, so if you look at your periodic table, you'll see that boron as well as aluminum will have an open shell. So boron, they can usually make 3 shared bonds. And if you're trying to form a covalent bond between boron and fluorine, then that means that it will share electron pairs with fluorine. So fluorine is a halogen, so it will form 1 bond with boron each time. So in total, they will share 3 pairs of electrons, meaning that you only have 6 electrons around boron, and that's okay. You can also draw this differently. So instead of drawing the electron pairs between boron and fluorine, you can draw them as bonds. And right now, we would still fill in all of the electrons. But as we get more familiar with OChem, we'll just know that fluorine will have 3 lone pairs no matter what. And then eventually, after I tell you, you can start leaving those out. Now, even though boron is happy with 6 electrons, it can also accept a pair of electrons to complete an octet. So, for example, if you have NH3 ammonia, so we're going to use an arrow to show flow of electrons. So the electron pair from nitrogen will flow towards the boron, and that will form a covalent bond. So let's draw the product here. All right, so that shows the covalent bond. So this is the covalent bond between boron and nitrogen. And let me ask you a question. So are we done with this structure shown here? Are we missing maybe anything on the structure? One big thing in OChem is that you shouldn't forget your formal charges. Whenever you draw your product, always ask yourself, is it missing any formal charges? So in this case, we are, right? So boron usually has 3 valence electrons. And here, you're going to subtract 4, which is the number of electrons directly attached to boron. So that's these 4 right here. And that means boron is going to have a formal charge of -1. And we started out with 2 neutral compounds, meaning that in the product, it should still add up to being neutral. So we need to take a look at that nitrogen. Neutral nitrogen has 5 valence electrons. And here we have 4 valence electrons. So 5 minus 4, we get a formal charge of +1. And now if you look at boron, let's point to the boron. This now has octet. it has 8 valence electrons. Just always remember that boron, it's pretty finicky, right? So it's kind of happy with 6 with 6 electrons, but it can accept one more pair to actually have octet. So it kind of flip-flops between these two states, and that's what usually drives reactions when you actually have borons and aluminum. Next, let's talk about Lewis structures. Lewis structures were important in GChem, and they're still important here. They show the connectivity and the locations of all bonding and non-bonding electrons and formal charges. However, Lewis structures do not tell you anything about the 3D arrangement. So in order to draw your Lewis structure, make sure you follow the Honk 1, 2, 3, 4 rule if you have a neutral compound. You always want to maximize the number of bonds without breaking the octet rule, because that makes your compounds more stable. And whenever necessary, always assign formal charges to any charged atoms. Remember, in OChem, we do formal charges for individual atoms. We don't really do the net charge of a molecule. Let's look at a couple of examples for drawing Lewis structures. I'm going to talk about 2 different methods, the GChem way that you're used to, and the OChem way, which is a shortcut. And you can see which one you're more familiar with. And as time goes on, try to transition into the OChem way because it really does take less time. So the first example says to draw the Lewis structure for CH3Br, methyl bromide. And if we were to use the GenChem method, I think some of you were taught to calculate the total number of valence electrons and then arrange pairs of electrons around each atom until you have octet. Then if any atom doesn't have octet, then you add a double bond using a lone pair. So let's start from the beginning. Let's calculate the total number of valence electrons. Carbon is 4, 3 hydrogens is going to be 3, and bromide is a halogen, so that's 7. Total 14 electrons. And you have carbon, bromide, hydrogen, hydrogen, hydrogen. So we have 14 electrons to fill. So this is going to be the arrangement that makes the most sense because we see that all of the atoms have octet. And if we count the number of pairs of electrons, we have 1, 2, 3, 4, and then 3 here. So that's 14 electrons. And when you're drawing Lewis structures, make sure to show all non-bonding electron pairs. And for some students, I think you use straight lines to show lone pairs. You could do that in GenChem, but in OChem we do formal charges. So you don't want to confuse one of the electron pairs for a negative charge. So make sure you don't use lines for lone pairs in OChem. Now let's look at the shortcut method, which is the OChem way. So carbon can form 4 bonds, hydrogen 1 bond, and bromine, halogen 1 bond. So there's really only one way to do this. Since you have 3 hydrogens and 1 halogen, you have to arrange them around that central carbon atom, right? So this is how I would tackle it using the OChem way. I personally think it's pretty straightforward, and I hope that you get used to it over time. Let's tackle example 2, drawing the Lewis structure for ethylene, which is CH2CH2. Using the GenChem method, we say that the 2 carbons, they have 8 valence electrons. And then the 4 hydrogens, they have 4 valence electrons. So that's 12 electrons total. And we need to arrange it such that we use up the 12 electrons and have octet. So this really would have to be the skeleton of the molecule, but you see that we only account for 10 valence electrons, and we're missing 1 additional pair of electrons between the 2 carbons. So carbon didn't have octet, and with the extra pair of electrons, now they do. They have 8 valence electrons. Let's see how this would work with the OChem method. So carbon has 4 bonds, hydrogen has 1 bond. So for this to work, carbon is going to form 1 bond to each hydrogen. You can't really put the hydrogen to the right of the carbon because you would cap off the molecule. So you would have to do it this way, and 1 additional bond in between the 2 carbons would then give it octet. So after those 2 examples, which method do you prefer? The GChem method or the OChem method? Usually I would take a poll in class, but since we're doing a remote format, we're not going to do that. But think that to yourself and maybe discuss with some of your classmates next time you see each other online. And let's look at example 3 now. So example 3 is kind of special because we're looking at somewhat of an ionic compound, right? We have a sodium, which is going to be positively charged, and this is called an ethoxide. You don't need to worry about the names yet. That's going to be negatively charged. So this has a combination of covalent and ionic bonds. The ionic bond is between sodium and ethoxide. So let's just first draw the sodium cation and then try to draw the ethoxide. So we know that we have overall a negative charge, and we have a CH2, a CH3, and an oxygen. Usually in OChem, we try to write it in the way that the structure is seen. So carbon, we know that they usually have 4 bonds. So we can draw an H here, an H here, and then the O should be here because of the way it's currently written. So the carbon's in the center. And then usually if you have 2 carbons in the same molecule, a CH2 followed by a CH3, they're joined at the carbon. Cannot be joined at the hydrogen because hydrogens can only form 1 bond. And then we fill in everything else. And right now, as the molecule currently stands, we see that both carbons have octet, right? And the oxygen right now only has 1 bond. So a neutral oxygen has 2 bonds. So it kind of tells us that maybe this negative charge, it's supposed to go onto the oxygen. Let's first try to calculate the formal charge for the oxygen. So for this oxygen to have octet, it needs to have 6 valence electrons and then a bond. So if we're doing the formal charge math for this, it would be 6 minus 7, and that's going to be -1, which is perfect because this ion overall is going to have a negative charge. So the negative goes onto the oxygen. All right, so that's how you should draw the Lewis structure for sodium ethoxide. Let's look at example 4, where we have a positively charged molecule, CH3CHOH+. So we can do this using the GenChem method, right? You can try this on your own time. If you have 2 carbons, that's going to be 8 valence electrons. 5 hydrogens is 5 valence electrons. And 1 oxygen, that's 6 valence electrons. So in total, that's 19 valence electrons minus 1 for the positive charge. So that's 18 valence electrons total. You can try to do this, the GenChem method. I'm just going to go for the OChem method. We're going to first draw the molecule that the way it is written, right? So we have a CH3. In OChem, we try to make it pretty straightforward most of the time. So we have a CH3, and then we have a CH, and then we have an OH, right? So that's the way it is currently drawn. So now we can try to put those 18 valence electrons onto the molecule, decide where we're going to put them. So we have a CH3, so that's 1, 2, 3, 4, 5, 6, 7. So that's 14 electrons accounted for. We have 2 more lone pairs. So where should we put them? We do have the option of putting both lone pairs on oxygen, right? It is possible for oxygen to have those 2 lone pairs and therefore have octet. Now keep in mind, in organic chemistry, carbon is generally the only second row atom that's not boron, obviously, because boron can have incomplete octets. But carbon, when we're talking about that Hunk 1, 2, 3, 4 rule, right? Carbon is the only one where it is possible for it to not have octet. So in this case, carbon has 3 electron pairs, 3 bonds. So that's 6 total electrons, but carbon can exist this way. So we can give it a positive charge, right? And we know that it's going to have a positive charge because carbon, regardless of whether it has a plus charge or a negative charge, it's always going to have 3 bonds. So let's do the formal charge for it. So it's going to be 4, which is the neutral carbon atom, minus 3, which is what we currently see, and you get 1, which is the formal charge of carbon. Now it has no lone pairs, right? With the lone pair, if that carbon had a lone pair, it would have a negative charge. Now, is that the only place where we could put those 2 lone pairs for oxygens? Can you think of another way, another place for us to put those 2 lone pairs where it could still work? So I want you to pause the video right now and actually think about another possibility. So pause the video right now. So the second possibility is going to look like this. So the skeleton of the molecule doesn't change, right? The backbone is still drawn the way that it is written. But now, if we choose to give the carbon octet, we can move one of the electron pairs from oxygen into a double bond. So we can draw a double bond here. So oxygen will still have one of the lone pairs, right? So now the carbon is neutral. So let's do the formal charge for oxygen. So it's still going to be 6 for neutral oxygen minus 1, 2, 3, 4, 5. So that's going to be 1, which is going to be a positive charge, right? So you can see that in both of these cases, this molecule and this molecule, they do not stray away from the positive charge that's shown in the question. So in these two cases, these two molecules, they're known as resonance structures. Now, the above molecule can be represented by more than one Lewis structure, and they're resonance structures for the same molecule. Resonance structures differ only in the arrangement of electrons, not in the connectivity. And the actual structure of the molecule is a resonance hybrid of the two structures that are drawn. So what does all of that mean? Okay, whenever we have resonance structures in OChem, we will represent them a certain way. So we have resonance structure on the left, let's fill in the lone pairs. We can move an electron pair to form a double bond and draw a double-headed arrow between two structures that are resonance structures. And we show the other resonance structure on the other end of it, right? So that's the lone pair that's left on the oxygen. You can go back and forth between the two, right? If you just move the electron in the double bond back onto the oxygen, then you would have the resonance structure that you started out with. We also put brackets to show that these are resonance structures. A lot of students forget the brackets. Make sure you do include them to show that these two are resonance structures. Now, the tricky thing about resonance structures is that a lot of students think of it as this structure rapidly converting to this other structure and then back and forth. That's not what this is. That's called an equilibrium. Equilibrium is not the same thing as resonance structures. When we show these two structures and we put a double-headed arrow between the two and call them resonance structures, what we say is that the actual structure is in between what's shown here. It could be that this double bond here, it's not a double bond or a single bond. You can think of it as a 1.5 bond. And this carbon here, it has a partial positive charge, not a full one like in this resonance structure, and it's not neutral like in this resonance structure. It's sort of a half positive charge. Same thing applies to the oxygen. It also has maybe like a partial positive charge. What you have in real life is something that's in between what's shown. We've already seen a few different types of arrows so far, and I just want to do a review on the kinds of arrows that we can see here in OChem. The first being resonance arrows, right? These are double-headed arrows, and these are not equilibrium arrows. Equilibrium arrows look like these, right? You have two arrows, one pointing to the left, one pointing to the right. That's an equilibrium arrow. A reaction arrow you use for chemical reactions, and it's just a regular arrow pointing in one direction. Now, something that's new in OChem, these are called curvy arrows or curved arrows, and they show the movement of a pair of electrons. So these are curved, and they show the direction the pair of electrons are moving. So that's a full head in this arrow. Whereas with a fishhook arrow, it's the movement of a single electron. So you have a half head for that arrow. We're going to be seeing resonance arrows quite a lot, and we're going to see curvy arrows or curved arrows a lot in this course. Now let's go back to the resonance hybrid. The hybrid is essentially the in-between structure or the real structure represented by a combination of the resonance structures. So let's take a look at the two resonance structures again. Right, so if we're trying to draw a hybrid, then what we will end up with is an in-between, a hybrid of the two structures that we have on top here. So whenever you have a bond forming, you need to show that in your hybrid structure, right? It's between the carbon and the oxygen. So you're going to use a dotted line to show that a bond is forming / breaking. And if you have a positive charge in only one of the resonance structures, then you're going to write a partial positive on the atom that has that partial positive charge. And you also have that for oxygen, right? And for resonance hybrids, we always leave out the electrons. Because as you can see, the electrons do move around, so they can be hard to represent. A few important things about resonance structures. When you think of resonance structures, know that they are not real structures because an individual resonance structure does not accurately represent the structure of the molecule itself. Only the hybrid tells you everything about the molecule. And like I mentioned earlier, resonance structures are not in equilibrium. They don't convert from one to the other, right? What you have is the hybrid. And resonance structures, they are not isomers at all because isomers differ in the arrangement of both atoms and electrons. However, resonance structures differ only in the arrangement of electrons. So let's look at some examples here. So let's look at these two pairs of molecules and try to determine whether they are resonance structures or whether they're isomers. All right, so let's look at this first pair. So we're going from a triple bond to a double bond. And to go from one to the other, we can draw a curvy arrow to show the movement of electrons, right? So we're moving the triple bond onto the oxygen. The electron pair is now at a different location, and all of the atoms, they still have that same orientation. So these two, they must be resonance structures. Let's move on to the example on the right. So let's look at where the differences are. And there are a couple here, right? So we have the hydrogen moving from the oxygen onto the carbon, and we also have a double bond that moved around. So because we have both differences in movement of atom as well as electrons, so this must be an isomer. And you can see that these two also have the same molecular formula because they have the same number of all of the atoms shown. Now, going back to the two resonance structures from earlier, we want to understand that resonance structures are not equivalent. Even though we represent both of them in the hybrid, one of them is going to look more like the hybrid than the other. And that's because of quite a few factors. And I want us to look at these factors before we try to apply it to this example here. So let's go to the next page, right? So every time we're looking at resonance structures and comparing them to see which one's the major resonance structure versus the minor resonance structure, there are three things that we look at, and they're listed here in order of importance. That's very, very important here, because point number one is going to be weighted much more than point number three. And a lot of students forget that, even in second semester OChem. So looking at rule number one, if we have a resonance structure that has more covalent bonds and fewer charges, that will be considered to be more stable. Rule number two, remember, is slightly less important than rule one. Rule number two says that if you can have octet in every atom, we will think of that as being more stable. And rule number three, which is really the tricky one here, it's the least important, but for some reason, rule number three is the one that all students remember, so they will jump to rule number three before they consider rule number one and two, even though rule number three, you know what? It's not that important. So if rule one and rule two says that a structure is more stable, but it breaks rule three, it doesn't mean anything. So rule three states that resonance structures that place a negative charge on a more electronegative atom will be more stable. And a lot of students, whenever they see a positive charge on an oxygen, they right away say that's the minus structure, and that's just simply not true. So now let's go back to our example. And I have this table here so that it's easy for us to go down our list. But note that this is in order of importance. So we're going to start by counting the number of covalent bonds. So in the structure on the left, let's count. I count 1, 2, 3, 4, 5, 6, 7. And the structure on the right, I count 1, 2, 3, 4, 5, 6, 7, 8. So that's 7 covalent bonds for the first one and 8 covalent bonds for the second one. So far, just based off of this first rule, the structure on the right is winning out. So we're going to put a check right here. And now we want to move on to rule 2, which is, do all of the atoms have octet? Do they? So looking at the structure on the left, carbon here, not that happy. It does not have octet. Oxygen here and carbon here, perfectly happy. All of them have octet. So let's write that down. Carbon here does not have octet. All atoms have octet. And so far, we're going to put a check mark again on the structure on the right. So moving on to the least important rule here, the one we care the least about. Do we have a positive charge on the least electronegative atom? So here we have the positive charge on the carbon, and here we have the positive charge on the oxygen. So yeah, for the structure on the left, we have the positive charge on the least electronegative atom, and for the structure on the right, the opposite is true. The plus charge is on the most electronegative atom. And so many students jump up at this point and say, oh, positive charge on oxygen, that's a big no-no. And then they say this is the minor structure. And that's just not true. This is the least important rule. Never forget that. Just because the positive charge is on the oxygen doesn't mean it's major, doesn't mean it's minor, okay? You have to look at the more important rules here. So you can see that for the structure on the right, it fulfills two of the most important rules. So that's going to be your major favored resonance structure. And all that means is that your hybrid, your real structure, is going to resemble your major structure more. So this guy here is minor. So what makes a good resonance structure? The best resonance structure is the most stable resonance structure. That's all. That's all we're trying to figure out here. So you always want to start by just counting covalent bonds, pretty straightforward. Checking whether everything has octet, again, pretty straightforward. And then the last thing is just to see where your charges are, okay? So moving back on to the next page, we do have a couple of additional rules. In organic chemistry in this course, the only atom that's allowed to not have octet will be carbon. And you will never, ever, ever, ever have +2 or -2 charge on any atom. If you do find yourself doing that with that kind of formal charge, it means you made a mistake. So just double check your work. Going into part 3, shorthand representations, you need to know that organic chemists are very lazy people. If we can save some time to draw a structure in a much more efficient way, we're going to. So that's why we have quite a few different ways of drawing structures efficiently. So the first one would be partially condensed structures. So in partially condensed structures, the bonds between carbon and hydrogens are not drawn out. Instead, the hydrogens are attached to a given carbon that are listed after that carbon in the same structure. So what we have here is a Lewis structure, and in OChem, with things being so repetitive with carbons and oxygens and nitrogens and hydrogens and halogens, it just doesn't make sense to draw a Lewis structure every single time. It's going to get old really quick. So what we do instead is we try to make it easier on ourselves. So partially condensed structures, you abbreviate the bonds between carbon and hydrogen. So you have CH3. You can write this as CH3 as well. I prefer to write H3C so that we see that the carbon is the one that's forming the bond and not the hydrogen. Then we have CH2. And we have CH2 again. Right, so each of these two CH2s represent this CH2 and then that CH2. So we have one more CH2. And then we have the chlorine. And we draw out the lone pairs on the chlorine. So we don't abbreviate this bond between carbon and chlorine because it is not a carbon-hydrogen bond. On to the next one. So we have a CH3 again. And then we have a carbon double bonded to an oxygen, right? We're not abbreviating the carbon-oxygen double bond because it's not to a hydrogen. And then we show the hydrogen that's directly attached to the carbon again. So that's a partially condensed structure. Let's look at the third example. You again have CH3. attached to the carbon that has a double bond to an oxygen. We show the lone pairs on the carbon, on the oxygen, I mean. And we have another CH3 group. Looking at the last example, we are starting out with a CH3 again. And a carbon to oxygen, like in the last two examples. And then a single bond to an oxygen. And then the oxygen has a single bond to the hydrogen. So usually we do not abbreviate bonds between hydrogen and other atoms. If you want to, you can, but in this example, you can see that I drew out the O bonded to the H. So you can see here that the bonds between carbon to other atoms are still shown. And this makes it easier for us to see the carbon skeleton as well as any branches that we might have. This is a pretty convenient way to save time and space when drawing structures. We have an even easier way called fully condensed structures to make it even simpler. In fully condensed structures, we don't show any bond dashes, and all the atoms or groups attached to a carbon are listed immediately after that carbon. If you do have complicated polyatomic groups and branches, they're shown in parentheses to show that these are together. So we're going to use the same examples from earlier, but now we're going to convert them into fully condensed structures. So in this first example, right, so we still start off with the CH3, but now we have three sequential CH2 groups, and we're going to show that. We have a CH3, and then we have CH2, but we have three of them, which is why we put the CH2 in parentheses, and then finally chlorine. And here we don't need to add the lone pairs because these are fully condensed structures. Looking at the second example, it's a similar idea. We start off with a CH3. And with fully condensed structures, we have very specific ways of writing out functional groups. So this right here, the carbon double bonded to the oxygen, and then single bonded to a hydrogen, that is an aldehyde functional group. And we'll talk more about that later. So in this aldehyde functional group, we have a specific way of writing it. We call this a CHO, and I always think of Harry Potter when I see this functional group, Cho Chang. And this functional group will always be represented in this manner. So if you do see a CHO and you have to convert it back to a Lewis structure, then make sure you don't draw this because I see this a lot. So students will see CHO and then they would draw a carbon to an oxygen to a hydrogen. Now, what's wrong with this Lewis structure? So carbon here, it doesn't have octet, right? And usually if carbon doesn't have octet, it still has to have 3 bonds because then it has a positive charge. There's something just not right with the carbon only having 2 bonds. The third example has a different functional group. This is called a ketone. So it's a CH3 and then a CO to represent the ketone, as well as another CH3. Draw this here. So when you see this functional group, also make sure to not draw it this way, where the carbon has only 2 bonds. Okay? And in the last example, we have a functional group here called a carboxylic acid. And that will always be shown as COOH. I do see other textbooks use CO2H. That's fine too. These are both acceptable ways of writing out that functional group. And make sure that when you convert it back to the full Lewis structure, you don't try to draw a peroxide functional group, which is a single bond between 2 oxygens, right? The carbon here still doesn't have octet, right? It only has 2 bonds. Something's not right. You will need to draw it differently, all right? What I love about these fully condensed structures is that they save a lot of space and they're really easy to just type out in a Word document. However, they're mostly useful only for pretty much simple structures. If it's too complicated with a lot of branching, then fully condensed structures leave out too much information. So you can only use it for something that's rather simple. In the previous shorthand representations, we don't really have any kind of three-dimensional information. So in OChem, three-dimensional information is pretty important, which is why we also have 3D structures. And these give us three-dimensional orientation space. So let's look at an example. We still have a central atom, usually that's carbon here in organic chemistry. And we have 4 atoms surrounding that central carbon atom. And we can have wedges to show that the atom is coming towards us out of the plane of the paper. We can have dashes to show that the hydrogen is going behind the plane of the paper. And these two are just regular bonds, so they are in the plane of the paper itself. And next we have bond line, or also known as skeletal structures. And this is really going to be the most commonly used one. And I want us to get used to the bond line structures as soon as possible, because you really do save a lot of time and space as well when you're using bond line structures. This can be a tricky one to get used to. So in bond line structures, we omit all of the carbons and hydrogens. Instead, we only show the bond between carbon atoms themselves. And each of the vertices, each angle, represent a carbon atom, and they're assumed to be bonded to just enough hydrogens to complete their octet. So you don't show any hydrogens, you just draw a carbon, and then you just go from there. Also, the end of any line that is not attached to a written atom is attached to a carbon. So let's look at examples. So these are the same example molecules that we used in our previous examples, but now we're trying to draw bond line structures. So let's look at this first one right here. So we have 1, 2, 3, 4 carbons, and then a chlorine. So paying attention to points 1 through 4 here, we're going to just draw the bonds between the carbons. So we have 4 carbons. Let's number them. So we need 4 points, essentially. We're going to start with this. This will be carbon number 1. 2, so this is carbon number 2. 3 is carbon number 3. 4, this is carbon number 4. And finally, we do show the bonds to other atoms when they're not hydrogens. So to chlorine would look like this. And then we fill in the lone pairs on chlorine. And this last point here, number 4, the end of any line that is not attached to a written atom is also a carbon. So I want to point that out because some students get confused. They think that this is a carbon, but it's not, right? Because it's attached to a chlorine. So make sure you remember point number 4 as well. Moving on to the second example. So we're doing something similar here. We want to first find the carbons, and we have 2 carbons. So that means that we're going to have 2 atoms attached to one another. So this is 1, and that's 2, right? It's 2, right? And to atom number 1, we only have hydrogens. So we don't show any of the bonds on that carbon number 1. However, on carbon number 2, we see that we have a double bond to an oxygen. So we have to show that. Right, and we leave out the hydrogen that's attached to carbon number 2. I've seen some people draw it just because it's an aldehyde, which is a special functional group that you will learn about later, but it's perfectly fine to just leave it out. The third example has 3 carbons, 1, 2, and 3. So we can first start by drawing in the carbon of that bond line structure. So we have 1, 2, and 3. So you can see that on carbons 1 and 3, you don't have to draw in anything, right? Because you only have bonds to hydrogens, and the bond to the carbons, they're already shown. However, on carbon number 2, you do have a double bond to an oxygen, so you do have to show that. So we're going to fill that in, and that's what example 3 is going to look like. And example 4 has 2 carbons. I'm going to number them 1 and 2. So same as the second example, we're going to start by drawing just those 2 carbons. Then we'll number them 1 and 2, just so we know which one's which. So on carbon number 1, you have a bunch of hydrogens, so you don't have to draw anything on that carbon. But on carbon number 2, you do have a double bond to an oxygen, a single bond to an oxygen, and then a hydrogen here as well. So you can see here that I did not draw a bond between the oxygen and the hydrogen. That's a bit more advanced. You'll get used to just seeing OH groups without a bond in between them. You can draw out the bond here as well. Both would be correct. I'll just write out the other one just in case. All right, so either way is fine. So these bond line structures, they focus attention on the shape of that carbon skeleton, and they also save time and space. They're very, very useful for very complicated compounds. So compounds that contain rings or compounds that have a lot of branching. If you use skeletal or bond line structures, there's not really any room for confusion. It is pretty common in organic chemistry to combine more than one type of structure, just because sometimes a combination of different shorthand representations it's the most efficient way of letting people know what structure you're driving at. So let's look at our first example. So we still have a central carbon atom. And you can see that attached to the central carbon atom are 4 separate groups. You have a CH3 and a CH2CH3. And these methods of representations, they're condensed formulas. So here you have a combination of 3D as well as condensed. And for now, we're going to draw in the lone pairs on the chlorine until we get more advanced. Another way of combining things, you can also have this structure. Right, so here you have a bond line or skeletal structure, and you also have a condensed representation. So these are all acceptable combinations of getting your point across as to what your structure looks like. In organic chemistry, we care a lot about this idea, or rather entity, known as functional groups. A functional group is an atom, or usually group of atoms, with characteristics that are chemically and physically unique. So a functional group will always contain either heteroatoms or pi bonds, which are also known as double bonds. And then heteroatom is defined as anything other than carbon or hydrogen. And that might sound like a lot of stuff, but in organic chemistry, we're really only talking about nitrogen, oxygen, sulfur, phosphorus, and halogens. We rarely use any other chemicals or any other elements. And pi bonds are usually between carbon-carbon atoms or carbon-oxygen atoms. And you can also have triple bonds. Those are also known as pi bonds. And you can have them between carbon-carbon or carbon-nitrogen bonds. So why is it that when we have heteroatoms and pi bonds, we call them functional groups? Point number one is because they confer reactivity on the molecule. They give this molecule something that make them reactive. So for example, heteroatoms, they have lone pairs, and because of these lone pairs, you create electron deficient or electron rich sites on a molecule. And pi bonds are also electron rich, right? You have more electrons usually, and they're easily broken in chemical reactions. So let's look at these two examples here, right? One has a heteroatom and one has a double bond. So when you have a heteroatom, such as an oxygen, the lone pairs make that oxygen electron rich. And you might also recall that oxygens are pretty electronegative, so they're going to pull electrons away from the carbon. So the oxygen end up with a delta negative charge because it has the ability to pull more electrons towards itself. Carbon, on the other hand, because of its proximity to oxygen, it's going to have a partial positive charge since oxygen is pulling its electrons away. So you end up with an electron-deficient carbon. Generally, these heteroatoms, they do not have the same electronegativity as hydrogen or carbon, so you end up with an electron-rich site on the heteroatom and an electron-deficient site on the carbon atom. So now let's look at the pi bond. Whenever you have a pi bond, it is going to be electron-rich. So the pi bond itself, that pair of electrons on the double bond or the triple bond itself is going to be considered electron-rich, and that is also a functional group. When we're talking about functional groups, we usually leave out carbon-carbon and carbon-hydrogen sigma bonds, also known as single bonds. And that's because they're typically not reactive. They don't really do much. They kind of just sit there. So we designate them as R groups since we want to pay attention to the functional groups as that's where the change is occurring. We have the carbon skeleton, which is the unreactive portion of the molecule. And then we have the functional group, which is the reactive portion of the molecule. Let me give you an example. So let's say we have ethanol. So that's ethanol. And oftentimes if we're drawing ethanol and we're trying to represent it in a reaction, we can just represent this entire CH2, CH3 group as an R group. So we can say this is just ROH if we just want to refer to it in terms of its functional group. So now we're going to talk about a few functional groups that you will be seeing this semester.